My name is Hunter Prendergast. I'm working with the Adaptive Optics X96 project at Manoa. Our project essentially takes light and attempts to unbend it to get rid of interference that might occur because of atmosphere or anything in between the object being observed and the apparatus you're observing it with. Essentially, our setup will be a laser source that will emit a light wave through a culminating lens. It will bounce that light off from a deformable mirror. It will be redirected through a magnification stage, through a beam splitter, and divided between a Shack-Hartman wavefront detector and a CCD camera. The purpose of this research is to assess if a neural network can be used as a control algorithm for an electronically deformable mirror. The software system is shown on this side of the board. As you can see, the Shack-Hartman data is fed into the computer. Let me pause for a moment and explain that the Shack-Hartman is a wavefront detector. It essentially determines the geometry of the light incident on the front of it by observing how that light passes through a micro lens array onto a camera. The website will have more information on exactly how that operates. But the Shack-Hartman camera that we're using is a Thor Labs camera. It comes with an existing C driver library. We have used that driver library to create a two-dimensional array output of 81 floating point values. Those floating point values represent the z-axis deformation of the incident light. That data will be fed into a neural network. The exact structure of that network is still being determined. But the idea is to take the neural network and attempt to find a solution to how the deformable mirror must be manipulated to correct for any aberrations in the incident wavefront. So the neural network will perform its sets of calculations. It will be trained either through backpropagation or online training. It will be fed through a translation program, which will then feed the output to a voltage divider. This will be a piece of hardware that essentially takes a input of 200 volts DC and will create 86 outputs, each one with 256 discrete steps between 0 volts and 200 volts that will be applied to the 86 inputs of the mirror itself. The mirror will deform based on those inputs and hopefully unbend the light that's incident on it that is bent. So our goals for now are to first introduce a static deformation to the system and attempt to create a neural net either through existing structures or through new structures using a genetic algorithm to assess what might be the best geometry or linking of a neural network for this purpose. As you can see, this is a quick sketch. We plan to introduce a very simple deformation, something similar to that, possibly as linear as possible. And then if we can get the neural net to bend the mirror in the appropriate manner to flatten the wavefront, we plan to introduce a more complex static deformation, see if the neural network is capable of correcting for those deformations, and finally to introduce a dynamic deformation to the system using heat guns, fans, or some other method to constantly change the geometry of the incident light such that it would mimic real-world conditions for, say, a telescope trying to unbend atmospheric aberration. This is our actual hardware setup right now. This is a deformable mirror that we'll be using at first in the system. It is not wired in yet. We have to buy some more hardware in order to mount it, and we also have to finish wiring and programming the voltage divider. We have a laser source here that takes 5-volt input, generates a light which passes through culminating lens, through a filter to take down the intensity of the produced laser light. We're reflecting it off from a static mirror at this point just for alignment purposes and general testing, through the magnification stage, and then into the Shack-Hartman detector. Our laptop is not currently wired into the system right now, so you're just kind of seeing the setup in an unoperational manner. And that is, for right now, the Adaptive Optics project here at UH Manoa. Thank you.